In the structural mechanics case studies that we'll be doing in ANSYS, we'll be looking at the structural response of a bike crank and of a bolted flange subjected to loads. And to understand what is happening under the hood in these ANSYS case studies, we need to know what the mathematical model is that ANSYS is solving. In particular, we need to know what are the governing equations that it's solving, what are the physical principles embedded in those governing equations, and what are the assumptions contained in the governing equations. And the governing equations are based on 3D elasticity. So here in the big ideas in solid mechanics, I want to give you an overview of the principles on which, what the governing equations are, and the principles on which these governing equations are based. I won't do a detailed derivation because the equations are anyway coded into ANSYS. I'll try to give you an intuitive feel for what the equations look like and what the various terms mean. For those of you who have had courses in solid mechanics, one or more courses in solid mechanics, this will be a review of the key ideas that kind of brings together the major concepts. For those of you who haven't seen these ideas before, it'll be an introduction to the big picture, and hopefully it'll form a good foundation from which you can build further. The first concept I want to look at is the concept of normal stress. And if I go to a bar, okay, if I'm looking at a bar, and let's say the bar is being held over here and it's being subjected to some bending load here. So it's basically a bar in bending. And I'm looking at a very, vanishingly small chunk of material like that within the bar. In fact, I'm recycling this graphic from the big ideas in FEA, where we are looking at heat conduction within this little chunk of material. Now we are looking at the forces on this little chunk of material, because this tiny piece of, chunk of material is going to be pulled or pushed by the material next to it on all the faces, and it's also going to be sheared. And in fact, I'm interested in the forces on the faces, but I look at it in terms of a stress, which is force per unit area, in the limit as the area of these faces is going to 0. And if I draw out the stresses on the faces, I'll get something like that. Let me unpack this. So let me consider this face, and x is in this direction. So the normal to that face in the x direction, and I'll say the normal stress in that direction is, I'll denote it as sigma x. Similarly, I have a normal stress coming out, perpendicular to that face. So that face is being pulled, and the normal stress is sigma y, and then I have sigma z. So I have to look at planes in 3 perpendicular directions, and so I'll get 3 normal stresses. These are the shear stresses that are doing the shearing. We'll look at that next. And often, we'll consider this in the 2-dimensional context where, we are looking, let's say we are looking from the top, and this would be, this face would correspond to this face here, and that would be sigma x, and this face would correspond to this face here, and this would be sigma y. And in the 2D case, we would set sigma z equal to 0. That is, any stresses in the z direction would be 0 if we are considering stresses in the x and y direction. And if I want to know the normal force on this particular face, I would say it's sigma x, the stress, times the area of that face, and that area is, if this distance is delta y, since this is the y direction. Okay, so that's y direction. This here is the x direction, perpendicular to this face here. Pardon my chicken scratch. Similarly, this will be delta z. So if I take that normal stress and I multiply it by delta y times delta z, which will give me the area, that'll give me the total normal force with which that material next to it is pulling that face. And if sigma x is positive, it's pulling. You call it tensile stress. And if sigma x is negative, it's pushing it. The material next to it is pushing it, and it would be negative. So you would call that the normal stress. And we are looking in the limit as delta x, delta y, delta z tend to 0. So that's the idea of a normal stress. Next, let's take a look at the corresponding idea of shear stresses.